Okay, this video lesson is on how to assign oxidation numbers to compounds and elements in a balanced chemical equation, and then to write the uh, half reactions, oxidation and reduction half reactions. Okay, so first of all, what we want to take a look at is how to assign oxidation numbers for elements. This is very straightforward. Elements have all of their necessary electrons. They haven't lost any, they become charged particles, so they have an oxidation number of 0. So this magnesium, it's an element in this reaction, so is iron. So they both have an oxidation number of 0. Okay, so the charged particles here are found in the compounds, and so they have slightly different oxidation numbers. Okay, so what I'm going to do is I'm going to try assigning oxidation numbers to this compound right here, magnesium sulfate. So magnesium sulfate is composed of one magnesium. Don't worry about this. This is a coefficient, and it's only used for balancing a chemical equation. That can change if you have different chemicals in this equation. Okay, so it's just the compound that we're interested in, and there's two parts. We've got the metal or the positively charged particle, and the negative or the anion, which is the negatively charged particle. Okay, magnesium and sulfate. Okay, there's only one of each of these. Okay, although there's a subscript, the subscript belongs as part of this entire particle called the sulfate ion. Okay, and sulfate actually has, so there's only one of those, and sulfate has an oxidation number of 2 minus. So what we can do is we can actually assign the oxidation state to the other particle based on that charge. The anion is usually the one that there's no um, discussion about. It's usually the one that it's exactly whatever charge you'd expect it to be. Magnesium is in the second row, and it's always going to be the same charge. It's always going to be 2 plus when it's in a compound, and you can see that these two charges match up. Okay, so magnesium has an oxidation number of 2 plus, or otherwise stated, it has a charge of 2 plus. Okay, so we can do the same kind of thing here. Okay, in this compound, we have 3 sulfate particles, and sulfate is going to be the same charge no matter what compound it's in. And so I can just maybe show this as a diagram. So each sulfate is 2 negatives. So there's 3 of them. So each one of these particles is circled. So the total charge is 6 minuses. Okay. In order for a compound to exist, it's got to actually be neutral. So its positive charges must match its negative charges. So there are actually 6 pluses to match it. The only difference here is instead of having 3 particles, we only have 2 for iron. So as a result, we split these charges evenly into 2 groups. The first atom of iron, and this is the second atom or ion of these. Okay, so each one of those iron particles has an oxidation number of 3 plus, for a total of 6 plus overall. Okay, so this kind of work is pretty important because it allows us to figure out what charges we have. Okay, and once we figure out, excuse me, 3 plus, figure out what charges we have, we can start writing out our half reactions. 2 minus, this one is 0, 0. Now another way, just briefly, is if you've got um, subscripts, let's say, on each of these atoms, or even just on one, you can double check with something that we sometimes call the backwards crisscross. Okay? Where we take a look at the subscripts and we assign the charge to the opposite um, ion. So that 2 represents a 2 minus on this, and that the only thing you have to be worried about is that these 2 things match. Okay? And we know that sulfate is 2 minus. It's kind of a little check. And then this 3 is assigned to the ion over here. Okay, and that they match. So it doesn't always work. When you look at this one, there's only one sulfate, and technically, because there's no brackets, there's only one of these sulfates. If we did a backwards crisscross here, we'd be mistaken, and we think that this would be 2 minus, this would be a 1 plus, but kind of double check and the charges don't match up. So once we have the charges, we can write out our half reactions really quite easily. What we want to do is identify the particles that are changing their oxidation number or their charge. And we've got magnesium here. It's going from a 0 to a 2 plus. We can write that out. Magnesium is going from 0 to 2 plus. And the only last little thing we want to write down is the number of electrons that are being changed or being lost or gained. And we do that by figuring out what matching the charges on both sides of the equation. We got a 0 over here, there's no charge. We got a 2 plus over here. And we match that by including electrons. So electrons are negative. I'm actually going to put the 2 electrons on the side that is more positive, okay? Or closer to the positive end. Now we've got 2 pluses, 2 minuses, total charge is 0. That's 0 over here. And then we're done. Okay, so iron, it's also changing. Its oxidation state is going from 3 plus to 0. And so as a result, we can write out iron 3 plus, iron up on this side, balance the charge by putting in electrons, 3 negatives there, and now everything's all balanced. Okay. One little thing that I want to note is I didn't include the number of atoms that are actually in the original equation because it's actually easier just to work with one atom and kind of simplify things. But if I really wanted to and try to match it, I could say, well, these guys, if I triple this, it would look more like that original equation. And if I double this, it would look more like that equation. And the reason why we do that is we want the charges to match up. Because when we combine these half reactions, we don't want any electrons left over, so they got to be the same number of electrons. Okay, so that's kind of the idea. Now the last little thing that I will mention is how to figure out which one's an oxidation and which one's a reduction. This one's an oxidation, and there's a couple of ways to think of it. This one's the reduction. And basically the idea is if the electrons are on the right side, it's oxidation, and if they're on the left side, it's reduction. Another way to kind of look at it is, and I actually like using a slightly different way of writing it. Let's take a look at this one down at the bottom. So the iron 3 plus going to iron. I could write this a slightly different way because the electrons are still on this left side. And what's happening during this whole process is 3 electrons are going into the substance, and so reduction is gain of electrons. They're gaining them right there. Okay. Magnesium, what do we got there? Magnesium 2 plus. Electrons are over on this side. Okay. So those electrons are getting dumped off or being lost by magnesium. As a result, loss is, or lose electrons is oxidation gain. Electrons is reduction. That concludes the video.